funny.
I've never taken Chem 1.1. I just skipped it. I just went to the second one. But
Okay, what about it?
yeah, I mean, he has like all these like notes that we can fill in, PowerPoints we can fill in the blanks, and there's like online lectures and stuff, and there's online homework and like online test quizzes. I've never even opened up one of these sort of online.
Crazy. Who would have thought that he would have been able to
First
do
thing,
it?
why would you not just homework super easy? Use like a lockdown browser.
Oh,
But
yeah.
I'm just like jokes on you at a second.
You always have a second computer.
Oh, I spoiled it, man. Yeah, I just like pull my laptop over right next to me. Just have it all set up on my desktop.
It's beautiful.
I did,
Egg.
what class was that? Computer science, where you have like the modules and then you have the projects too. It was quite entertaining though, because I would do the practice module and like the assignment, and at the same time I would go to the library and then I would have my laptop open, do practice, do the same thing because it was the same question, and then you move to the next one. I mean, it took like 45 minutes a week, but then you didn't have to go to class. I was like, I this fun with it.
Which is nice.
Right?
I don't know what you're talking about.
Computer science class.
Do they teach real programming or just click the mouse?
Pretty much click the mouse. It was like Microsoft programs.
How do you think so?
Yeah.
Thank you.
Which I
Sounds
mean
like
was
MIS
helpful.
one.
Sounds like kind of a good class. Just like you put it in class.
No, it wasn't MIS. It was like actual computer.
Does that feel like
It's
kinda-
CSCI.
Ready
Okay,
for the
yeah, we're
weekend?
done talking.
Too long. Okay, prepare. I have 53 slides.
Okay.
And I'm trying to squeeze 2 lectures into one once again. So it will be a marathon. So, just a quick overview. And I really like interacting and asking questions and see feedback, but maybe not today because there are too many. So, physical chemistry, predicting outcomes of instruments, wavy nature of electrons, and applying it to small models. And we are going through the chapter on particle in one-dimensional box that we are looking from different aspects. Before we have found energy eigenstates, and I think everyone was happy to find the dependence of lowest available energy on the size of the box. Like smaller the box, larger the energy, and opposite. And then suddenly you very quickly switched to counterintuitive superposition and evolution in time that we are about to finish today for this model, but we will come back to it again. And now there is a third aspect of dealing with particles in the box. How to describe them in case size of the box is large enough. If the energy states are very close to each other and there are not enough fingers on palms to count them. If there are like hundreds of thousands of states, but we still want to tell something about this system. So how to deal with energies of quantum states if there is a large number of those. So it will be this point, and Alyssa should be best expert in the room, even maybe better than I am, about density of states. So it is a concept that I think everyone might have heard about it. So it's a concept that consolidates from discrete levels into something more continuously distributed. This concept, and then we will be ready to go from one-dimensional box to three-dimensional box, which is more realistic because our world is three-dimensional. So by the Three-dimensional blocks will be for next meeting, and today we will do density of states after I complete some of the images from last time. So we do not have the helper. I will be jumping between podium and the screen. The stuff that you see on the right side, the next work will be possible to do after we go through a new code this night. And it will be maybe not super quick, but quite easy. And I already have a plan for next work. It's not a secret, I will distribute it soon. Okay, so we are doing, we have done density metrics, and now we are coming to a new concept of density of states. After we finish with this little things from last time. So we were looking into distribution of probability as function of position and time, and we are exploring at 3 different times, which are most typical. And we want to obtain figures that will show probability distribution leaning to left side, right side, or in the middle. So there are contributions from ground state, excited state, and mixed terms. Mixed term appears with different signs or disappears completely because it is modulated by a cosine function. So in first and last line, we practice identifying the full square, and here we just put sine square out of brackets. So those are, after putting sine square out of brackets, one can try to plot this 3 functions and see if they remind what we want to see. Probability distribution leaning to the left or right. I'll try to be smart and use the advanced. Okay. So we start from the first one, where the sign here is the plus, and we try to plot the function. So cosine multiplied by 2. If we are looking on the length of our box from 0 to 1 to the full length, cosine goes from +1 to -1, and we multiply it by 2. If we add factor, if we just change axis or move the whole line out of half, right? And before it was crossing x-axis in the middle, now it crosses x-axis a little to the right. And then we multiply it by sine square. No, not yet. We are just taking square of this line. So where it crosses 0, it will be 0, and to the left and right, it will be positive. Right? So square of red line will be black line. And sine square will have a maximum in the center. So now we multiply black line by green dashes. So it will be 0 where either one of functions is 0, so on the edges or in the center. And if you perform this multiplication, it will be 0 here and there, and the maximum will be leaning towards left. Right? Now, if we practice the medium part, you will see a camel. So it's symmetric. It's equal probable here and there. And if you put minus sign, then it will be similar stuff, but the this function will cross 0 to the left side. Therefore, upon completing all procedures, the maximum will be on the right. Okay. So now you can predict motion of the wave packet in the quantized particle in the box without a computer, right? With pen and paper. Right? It is what you are seeing when you run this code. Okay, done. But please do not leave. So, this ugly stuff will be the last slide. Let me guide you through so that you get general idea, and then we'll go through details if you're curious. If you're not, you can just use time to take a breath before your next destination in your complicated schedules. So let's look on the blue part here and green part here. Question to Alyssa. What does it look like? What it reminds you from your career?
Bandgap?
Yes. Where should I put fingers to the bandgap, right? But how do you describe these lines? What is it?
It's density states.
But can you tell it in a lay language to all of us?
I mean, if it was... Well, put me on the
But
spot.
wait, I put camera. Okay, so you teach this class instead of me.
I'd rather not.
But just try to give some ideas. What is density of states just to your...
It's the chance that the electron's basically going to be in there. I mean, it's... I don't know how to... It's been a couple of years.
That's fine. That's a chance that electron will be there, but it's not position. X-axis is energy.
No, it's like orbital, I guess, but not really. Like
Chance that an orbital, that state of electron, is allowed to have certain energy, right? So that electron is allowed to have energy in certain range of energies, right? Agrees with what you would think. Okay. I need to quickly check if it is better. Okay, good. Sometimes it randomly jumps to different places. Okay, so this green and blue, according to Alice, is probability that electron is allowed to have energy in this range. And density of states, this distribution and permission for electron to have energy in certain state, is very, very specific for each chemical, for each molecule, for each material, and even for each nanostructure when chemical composition is the same but size is different. And density of states is like spectroscopy. Based on density of states, an experienced researcher can identify and make a deduction what was the original material. So it's a unique signature. Before one can solve this identification problem, one needs to get an experience and try to solve direct problem, how to get this signature out of the Hamiltonian, out of the chemical composition and shape of the structure that you're looking at. Okay. So in this figure that Alyssa helped us and recognized as something familiar, we will look only on the right side. So I will not talk about occupied orbitals for holes. We'll talk only about electrons, which are predominantly unoccupied. Only this side. And we will obtain density of states for one electron in one-dimensional box. And we know that the states are discrete, but if you assume that the box is very large and the states are close to each other, you will see a trend. And if you remember that energies are offset by the energy of each state is like n proportional to n squared, it means that next and next and next will be offset more and more and more, right? Which means that for a certain energy, the chance to have an electron with permitted energy in this range will be less and less and less. So we are going to get some decaying curve. And it will be not just hand-waving philosophical arguments, it will be strict mathematical derivation. But you already get the idea, right? The higher the energy, the less states are there. It's a summary of today's meeting. Oh, okay. Going to higher energies, density of states decreases. And mathematically, it will be only one line of derivation. We will need to take a derivative, and we can throw a dice and invite someone to take this derivative on the board if there will be time. If not, it's super easy for all of you. Okay. It's we are looking on this trend. Do not look on the second figure. The code that we will consider today in the lab will generate something more general. So it will generate density of states for any size of the box and for any dimensionality of the box. So the two density of states is, we already discussed it, how many states are permitted to exist in a certain range of energies. Okay. What do you see on the slide? Yes. And what else? Do you see anything in addition to steps? Ah, yeah, a stickman that probably wants to climb this ladder, right? What are the axes of this figure? I know I'm not the best drawer and not an artist, but probably I'm writing sufficiently good to recognize the axis.
Number of states?
Yes. And on X or Y?
I believe Y.
Okay, Y, and on the X?
Energy?
Yes, and it is reduced, its energy dimensionless. We divide energy of a given state divided by energy of ground state. So that it's a pathway of a lazy man to forget about all constants. Like if I forget, should I have Planck nominator or denominator? Should I have mass nominator or denominator? Is there a factor 2? If I want to forget, I just make a ratio of energy to the ground state. So what you would expect, it should be what we typically did, what it would be natural way of thinking is to swap the axis and put energy as function of of index of the orbital, as index of quantum state, right? So the first state has energy E naught, or if dimensionless 1. Second state has energy 4. Third state has energy 9, right? And now I just took liberty and swapped the axis. So I'm a little adjusting the logic, and instead of asking question, what is the energy of state number n, I am pretending that I'm this stickman I'm walking forward and looking backwards. So this arrow means I'm walking backwards. And if I'm staying here, I look how many steps are behind me. Like how many, here it is 3. How many steps I did climb by now? 2, 3, whatever. If I go further, I will climb more. And now this stickman counts number of accomplished steps as function of energy. Basically. So this concept is okay, right? Number of accomplished steps. Now let's follow the life records of this poor stickman. And when does he changes his mind about number of accomplished steps? At which value of energy he changes mind? Like when he walks between 9 and 16 here, he doesn't change the mind. It's still the same number of steps behind. But when he climbs the next one, he changed his mind instantly.
Constant square value of the natural number.
Yes, but it is he changes his mind instantly only at certain values of energies, which are actually the number quantum state and value of eigenenergy. So what would be interesting to us to make a connection, like to make records of life records of this stickman, and connect his mindset, like when he has spike of mental activity, when he actually climbs something and when he just goes forward. Okay? So we may want to take derivative of this step function, which will be 0 if we are on a steady plateau, and will be infinite spike if we are climbing, right? So I invite you to open the steps and derivative of the steps. So when we go from 0 to 1, there is a peak. When we have derivative from 1 to 2, there is another peak. When we have from 2 to 3, there is another peak. And it is nothing but derivative. Number of steps behind stickman in respect to energy, right? If the life of the stickman is just to walk forward in energy, right? So this derivative of states over energy will be set of peaks located at eigenenergies. Make sense? There are 2 limits. One limit, if our box is really tiny and the states are far from each other, then we are getting these spikes, and then we do not need the concept of density of states. Then we are safe to count them with fingers on one palm. But if the box is really wide, right, which will not change relative E and E sub n divided by E naught. But if you look for absolute energies, it means that the states are very close to each other and the spikes start overlap. Right? So there is a little trick. If they are so close and we want to see influence of one peak on the way how we see overall picture, one can replace infinitely sharp peaks with some shape with Gaussian shape. On one hand, it is a mathematical trick just to make continuous transition from this comb of many peaks into continuous distribution. On the other hand, you already know without any physical chemistry course that atoms are moving. And if this particle in the box is composed as set of atoms where electron can move and set of atoms where it cannot, right? Motion of atoms will bring some fluctuations of the size of the box, of the energies, and in average thermal motion brings broadening for each energy line. So it is quite natural to assign finite widths to each line. And then, if there is a finite width, it is easier to imagine continuous line, getting together all those things. And if we go from like 4 peaks to like 1,000, we can focus on a range from whatever 5 to 25 and count how many states are in this range. Like 2, 16, and 25, right? Or whatever. So number of states per energy interval, which goes, which agrees with this definition, dn over de. And it doesn't need to, in definition, density of states doesn't need to have a strict derivative with infinitesimal energy interval. We can make just wide interval, just number of states per energy interval. I think it is the same, just in a little uglier shape. Maybe the thing that to open here, who has ever worked or heard about delta function? 1, 2. Who has never heard of delta function? 1, 2, 3. Okay, about, and someone didn't give this, well, about half. So you already accepted and digested the concept of function with infinite pi, right? No one was objecting, which means everyone agrees, or everyone doesn't care. Mm-hmm. So this function with infinite pi spike is called delta function. So it's mathematical abstraction. And the step function is called theta function. Theta function is step, delta function is spike. Delta function is derivative of theta function. And otherwise, integral of delta function will be theta function. I'll show it on the other side. And here, if we accept this notation of delta function, there will be delta of E minus E naught, delta of E minus E1 or 4 times E naught, right? So the argument of delta function will have the energy of state. If the density of states is DOS, the number of states is NOS, almost like a nose. And here just a little reminder if you do not play with these functions every day. We may use it later in the course, but so delta is infinity if the argument equals 0, or if we have like independent variable minus constant, when it is equal to 0 means independent variable equals constant, and 0 everywhere else. So that's pi. Theta function is 0 when argument is less than 0, and 1 if it is above 0. Or if you have independent variable and constant, then if independent variable is bigger than constant, it is 1. If smaller than constant, it is 0. And then it is a convention. So by taking derivative of theta function, one gets peak. And by taking integral of delta function, which is like if you put integral of derivative, it will be theta function back, which means integral of delta function is a theta function. So these concepts of density of states and number of states are can be converted from one to each other through derivative and integration. I'm always forgetting that there is a oh, and even laser pointer. An easy life. So here is our derivative of number of states over energy interval. Number of states over energy interval is definition of density of states. On the other hand, we can describe it as summation of all delta functions, right? With argument of delta function being the energy of the state. And in the specific case, so this is more general, and here up it is for one-dimensional box with one electron, where state number n is same as ground state times n squared. Delta function, one of the typical representation of delta function is replacing it by Gaussian with certain width. And then you width parameter is chosen either by your artistic feeling or by temperature. Higher the temperature, broader the Gaussian. Now let's assume that we add together. So contribution from first state, contribution from second state, contribution from third state. Then it is this like count of several peaks, several delta functions, several Gaussians. And now the next logical step is to assume that we do either one of the following things. First, we increase the size of the box and states become closer and closer to each other so that the tails of Gaussian distribution start to interfere. Right? An opposite pathway that gives to the same conclusion. Keep the size of the box the same, but raise the temperature. So the width of each Gaussian becomes wider. So the tails of Gaussian starts to interfere. So if you increase width of each peak noticeably, then summation of this contribution will, like on language of spectroscopy, lines become not resolved. So they become to like fuse into some general unresolved structure. So instead of having two peaks, you'll have just area which is twice as higher than individual peaks, right? And the height of this line will correspond to how many states are in a given area. When states are very dense, when they're close enough, adding together these fat peaks will give higher resulting line, right? When we go to the energy range when states are far enough, but still thick Gaussians, the average height of this distribution will become lower. So the height of this summation will correspond to offset between energies. Make sense? And I invite you to activate your memory and prolong lifetime of your impressions about this idea, at least to today's evening, because we will be illustrating this concept in the lab. So it will be behind the code that we will practice. Okay. So what we did right now is most important conceptual, but where is glory of math and analytical derivation? By now it was all really cool and related to real research life, but it doesn't look like an answer in equations that one can sell and tell, here are trends in a short equation. So let's try to do it. And for one-dimensional box, it will be really simple and quick. For larger dimensionality, we'll try on Friday, and it will be a little longer, but still a lot of fun. So, suppose your box is huge, temperature is large, and we are not looking on levels as individuals. We just look at them being very close to each other. In average, let's just draw a function how the energy of state depends on number. And we will not put them as individual sticks or dots, we will just write it as a continuous function. So how does energy of state of a particle in a one-dimensional box depends on number? Huh? Square, right? So we draw a quadratic function. No cheating, only approximations. It's a way of a scientist. Now, do you know how to invert a function? Like if you have sine, how to make inverse sine or arc sine? Or if you have exponential, how to make the logarithm? You have the concept, right? For each function, there is an inversion. For square, there is a root. But if we do it graphically, if I do not want to stick with algebra and want just to draw functions, inversion of a function means mirror reflection in respect to y equals x line. So if you draw exponential that comes through 1, then logarithm will also come through 1, but on the other side of this median line, right? So for small values of argument, logarithm is negative. For values more than 1, it starts growing. Same here, same function. Can we do this mirror reflection for a square function? So mirror reflection of square will be square root. And square function grows. The higher the argument, the quicker the bigger the slope. For the square root, it is opposite. The higher the argument, the smaller the slope. Doesn't work. Okay. Other volunteers to take a derivative. Okay, then you good?
Yeah.
Please help. Next time, just remind me to select next one in the line if there are no volunteers. So, the number of states as function of energy is square root, right? So we already have number of states, but now we need density of states. Density of states is derivative of number of states over energy, right? Which means one needs to take derivative of the square root of the e to the power 1/2. You will regret that you didn't volunteer. It's very simple. Do you know the answer? Come on, you do. Just say yes. Do this, right? Super. Let's applaud to you. So he's so quick. He did it quicker than I could do it. I will do it a little in steps, telling that e to the power 1/2 is e to the power n. Derivative of e to the power n reduces the power by 1 and gives factor in front. And if n is 1/2, then we have minus 1/2 and 1/2 here, right? Okay. You didn't miss the logic. First step was that energy as a function of number state was square. Number of state as function of energy was square root. And density of state is derivative of square root, which is e to the power minus 1/2. Now, how to draw e to the power minus 1/2? What is it? Try to draw it in your notebooks yourself, and then you check. Does it look similar or different from what is on the next line? So we are drawing the function that was derived by Untitled. E to the power minus 1/2. I have a big curiosity. I will look first what you have. Like, what will be the e to the power minus 1/2 if energy is equal 0? As a little exercise, first you can draw a function e to the power minus 1. 1 over e. Can you draw it? You can. 1 over x. Good. Almost everyone. So 1 over x is positive, right? If x is positive, 1 over x is positive. When x is 0, 1 over x, 1 divided by 0 will be
Negative.
infinite, right?
Oh, is it? Yeah.
Well, it's a philosophical question. We are not permitted to divide by 0. And when x is equals infinity, 0. And everything in between is just a continuous line.
Yeah.
So if we take 1 divided by square root of argument, the dependence will be the same, right? It's just a little different curvature. So 1 over x is sharper, 1 over square root of x is a little not as strong, right? And now we just put e instead of x. So you have interpreted, like Yu has derived, and we all have interpreted what is the density of states of one-dimensional particle in the box. So if you have an instrument that measures density of state, and if you see this 1 over square root of energy, you can say, your system looks like particle in the box. Should it be like two-dimensional sandwich of semiconductor between insulators? Or maybe it is a oligomer of conjugated polymers? Let's check. So it's a signature of a one-dimensional box. And later on Friday, we will see, we will not wait Friday, tonight, we will see signatures of other structures. So I was lazy to redraw it from last time, but the question is there an instrument that measures density of state? And I think it is either 1 or 2 slides. So today we are a little better than last time. So which instrument will you use to measure density of states? Do not make suffering faces. Which scientific instruments do you know? Spectrometer, mass spec, good. NMR, what else? Huh? I do not know this. Okay, EPR, okay, it's good. What else? What?
UV vis.
Okay.
IR. Ramen.
Huh?
Ramen.
Raman? What is a favorite instrument in the analytical chemistry?
NMR.
What else? When you have like a cell with a liquid solvent, you put electrodes, sometimes you bubble gas.
Oh.
Oh,
What's the name?
Oh, I can't think what that's called.
You scan voltage,
Yeah, I know it.
measure
Yeah,
current,
electrophoresis. Is that?
something electric, yes.
No, it's like an electrode.
You. Okay, so it's a little homework. Please find the right word by Friday. So this.
by Friday or by tonight?
Huh?
Oh, electrolyte.
By Friday.
Whenever you feel comfortable. You need just to say just one word. It's not written. So when you do this unknown technique with unknown name, you get current as function of voltage, and when the system is getting oxidized or reduced, you get peaks. And it means that voltage is sufficient to pump an electron or withdraw electron to a quantum level. So when there is a quantum level, there is a peak. When there is a second quantum level, like second reduction, there will be another peak. So this technique gives you density of states. Another technique, which is even more precise, is so-called STM, scanning tunneling microscopy. When you put gold, it's all golden. You put gold substrate and gold needle. And in between you have sample. And then you scan voltage. And you put needle very, very close to your sample. So if the sample has energies which will be equal to the applied voltage, there will be peak. And this instrument can basically reproduce density of states that like computational chemist can compute or that physical chemist can predict. So there is a way to measure density of states.
Yeah, that's the last file.
Yeah, this one, you already are aware of this file, right? And start set book. Thank you for questions and attention. Looking forward to see you tonight.
Is it not just electrochemical
Electrochemical analysis.
Yeah, yeah.
Is there not a different name for it?
I could have sworn there was. I think we're trying to get the name of the cell. Yeah, that was literally the last lab we did last year.
So you see a little connections between different classes and different subjects, right?
I told you a couple of weeks ago, we did down in the basement.
Yeah.
That's fine. That's fine. I'll try my best to have a recording and share all thoughts.
Okay.
Three.